Hello, welcome to the channel. I suppose this is my turn to play with the whiteboard and discuss the differences between torque and horsepower. I will try and give this presentation in a manner so that you can come to your own conclusions as to what you think you need when it comes to modifying your engines to get the performance out of it that you desire. Now, from my perspective as a hobbyist engine builder, I need to know the differences between these two, because the modifications that are made to an engine require different approaches to get these results. This is the formula for horsepower, and we all know that it was derived by James Watt in his experiments. But I'm going to take this apart and show you the importances and how he got to this formula. On the right is the formula for work, which is a force applied over a distance. Now, James Watt worked out that a horse could perform a task of lifting 550 pounds every foot per second for 60 feet. Now, while this may seem low, the attribute that this was accounted for was that this is sustained work over 8 hours. The horse could indeed lift more, but it would put undue stress on the horse and would effectively limit its life, and also give the potential to induce injury. That is how the 550 pounds being lifted 1 foot per second for 60 feet came from. Now, the work is 330 foot-pounds, which is effectively moving 550 pounds 60 feet. Torque is a force, and this force is applied in a rotational manner. So, to apply torque in the proper form that it needs to be, for an engine to be qualified as being able to apply 1 foot-pound of force through the unit measurement of torque, it needs to be able to move a bar that is 1 foot long and have on the end of it 1 pound, and it has the capacity of moving that bar at a rate of 1 foot per second for the entire duration of 360 degrees. Now, when we take the circumference of the circle that would be traveled from the end of the 1 foot bar, we wind up with a distance of 6.283 feet, which is the requirement distance that is traveled when one revolution is complete. To complete the conversion for our constant, we then take our work, which we've found to be 33,000 foot-pounds over the course of 1 minute, and we divide it by the distance that is travelled in one revolution of our imaginary 1 foot bar. And that's where we get to our 5252. To prove that the formula is correct, we can now use our basic numbers that we were using before. We can use 550 foot-pounds of torque, and we can apply it over a rotational measurement of 9.55, which gives us the circumference distance of a total of 60 feet in 1 minute. And when we divide that by 5252, we wind up with 1 horsepower. Alternatively, if we change our RPM so that the distance in which our rotating wheel, the circumference is 1 foot, will now mean we have to do 60 revolutions in 1 minute. We will travel, the exterior circumference will give us a distance of 60 feet in 1 minute. We now only need to apply 87.6 foot-pounds of torque to equal 1 horsepower. Now this formula is a formula for horsepower, but it does not include RPM. What it is using is cylinder pressure, displacement, and power pulses. The displacement is highlighted in red. Now, when using the formula for Planck divided by 33,000, the important thing to consider is the number of power pulses. Now, power pulse is the power stroke of that particular engine. Now, in a four-stroke, it requires four-stroke engines require two revolutions to complete its entire cycle. So the formula for the power pulses of that will be divided by 2. Hence a four-cylinder engine will have only 2 power strokes per RPM. Moving on to your 2-stroke, all rotary or a single action steam engine, the RPM and the power strokes are equal. So that is, you only need to apply the RPM as it is as a whole. Now I'll put this up for an extra. It doesn't really apply to any automotive engines, but it does apply to a steam engine that you will see on a steam train. And this is called a dual action steam, and this is when the piston will be forced, piston will have compressed steam on both sides of the piston. So throughout its entire revolution, it will see both a power stroke going down and returning coming back up. So when we break Planck down and we apply it to our theoretical engines, I've simply come up with a very simple one, which is 150 psi, which will be working over a 15 cubic inch engine, which works out to be just under 250 cc's. So in a four-stroke application, 150 psi cylinder pressure, and this is, when I say cylinder pressure, we're talking about what's called brake mean effective pressure, which is what I'll get into next. But at the moment, brake mean effective pressure times the displacement, 15 cubic inches, and then for our four-stroke, we apply our power strokes. So in this case, I've used an RPM rating of 120. As said, this is just theoretical, but the point to work out, and the bigger one, is when you look at the horsepower readings of all 3 engines. The 2-stroke has twice as much the horsepower as a 4-stroke, even though it has the same cylinder pressure and the same displacement and the same RPM. It'll produce twice the horsepower. The steam train, which has the dual action on it, will produce twice the horsepower of a 2-stroke and 4 times the horsepower of a 4-stroke. Alright, 2-stroke versus 4-stroke. When it comes down to power, it is in favor of the 2-stroke, and it simply comes down to this underlying formula. Now, cubic inch times RPM divided by and we look at both numbers, if it's a 2-stroke 1728, that is a simple formula which is simply converting cubic inches into cubic feet. When we do for the 4-stroke, because there is 2 revolutions required for the entire engine to consume its displacement, it is cubic inch times RPM divided by 3456. Now, using this formula and split in this way, we can see that a 2-stroke and a 4-stroke that have the same engine displacement, the 2-stroke is going to make twice the horsepower because it is going to consume twice the air and fuel. So, just a quick summary on this. Torque, which is a force, which is related to cylinder pressure, which is cylinder force, which comes under our brake mean effective pressure, BMEP. And then on the other side is horsepower, which equals airflow. To change or to increase horsepower, you increase the airflow through the engine, so you need more air and fuel, which will give you more energy that the engine is going to be supplied, so the output is going to be naturally higher, and it's processed in the same amount of time frame. So to increase torque, we need to increase our brake mean effective pressure, and as a result we increase our torque, and because of this torque increase we increase horsepower. Now, focusing on horsepower alone, we don't increase the torque, we just increase the RPM in which torque occurs. This ultimately leads us to increasing horsepower, because we are increasing the airflow through the engine because the torque is occurring at a higher RPM. Now, power is work divided by time. Now, this one is, and should have put this symbol up, or the relation to what it is, but it is in relation to seconds. So let's put a little bit of a scenario, and we'll put some things on, and you'll understand a little better as to what are the requirements, or what's more important. Are we needing a force, or are we needing power to accomplish our goals with performance? Putting some context to these numbers, we're going to apply them over a quarter mile time and give ourselves a pretty lame 15-second quarter mile time. Now, the purpose of this is to show that the force is going to remain, is one of those constants that we can change, and because we can change that constant, which means our work constant for the power is going to change as well. To decrease the time frame in which the quarter mile can be done, we need to increase the work rate, and if we go up to our work formula, the distance is set, so that means the only way to decrease the time frame that we can complete our quarter mile time is to increase the force. Interesting enough, when we apply that, the power that is given over that time frame does not change. The power requirement to do the work, namely, as the work rate goes up, the time in which it is completed by comes down. So power does not change. So this may highlight the confusion as to why people pursue horsepower when they should be pursuing force. And it's the simple confusion that horsepower is work over 60 seconds, which means 60 seconds is a time frame that is set. So when we increase horsepower, what we're doing is that we're increasing our work in the given phase of 60 seconds. So that means our horsepower will rise because both objects of force, which would be your torque, distance being our quarter mile time. So to decrease our quarter mile time, we need to increase the force, but in doing so, and when it is applied over 60 seconds, horsepower naturally increases with it. So now we're going to venture into gears, because here's another avenue into why they talk about, when you change down gears, you go into the higher RPM and you access the horsepower. No, when you down change, you you multiply the torque output of your engine, and that's what gives you more force, which gives you greater acceleration in the lower gears. So perfect example is, we'll do the basic, everyone knows 52 RPM, horsepower and torque are exactly the same. So in this example, 300 foot-pounds at the engine, 300 horsepower. When you do that in a gearbox ratio of 3:1, and then they go through the final drive, so your diff ratio of 4:11, you wind up with an output, so at the hub, you wind up with 3,699 foot-pounds. And that is just pure force to accelerate the car. That's why in first gear, when you mash that gas, that's why you are slammed back into your seat, because you are having almost 3,700 foot-pounds of force being applied to the tires. And when we then go and do the same ratio, and we work out the speed in which it's happening, so what we're doing is that we are reducing the speed. So we're going from an RPM of 52. When we go through the gear ratios, the final drive, the final axle speed is only 425.95. Now, interesting enough is that when you do the calculation for horsepower, it turns out to be 300 horsepower. So what happens is that all we're doing is, on the what we've demonstrated is it's called the conservation of energy. So as we established before, horsepower is an energy reading. So the energy output of the engine when going through the gearbox and through the drivetrain does not change. The only change that you'll ever find, which is into your gear ratio, when you go on a dyno and you wind up with power loss, it is simply the power being absorbed by having to accelerate the wheels, the tires, the axles, and turn the gears and the drive shaft, and turn the gears inside an oil-filled gearbox. They are the only times that effectively you lose horsepower, which really just comes from the fact that it is the force being lost by having to drive those components through through the fluid in the gearbox and the diff, and having to again through the CVs and accelerate all of that metal.